The history of the Second World War is often recounted through grand strategic movements, the movements of armored divisions across scorched earth, and the agonizing calculation of casualties.
Yet, beneath the noise of the tank treads and the scream of diving aircraft, a silent and equally critical war was being fought.
A conflict between deep-seated military experience and the disruptive, lightning pace of material and electrical science. For decades, the high commands of Europe had clung to military dogma forged in the mud of the Great War. Doctrines that prioritized heavy armor, massive manpower, and slow, grinding attrition. This rigid experience was suddenly forced to confront a world where engineers and physicists operating out of laboratories and hastily converted industrial sheds were creating tools that rendered established strategy instantly obsolete. The atmosphere during the summer of 1940 was thick with impending doom, particularly over the British Isles. The continent had fallen with terrifying speed, proving the superiority of the Blitzkrieg methodology, a strategy built on speed, maneuverability, and massed surprise. The British military command, steeped in tradition, knew that their ability to fight relied entirely on preventing the Royal Air Force from being annihilated on the ground. The prevailing wisdom suggested that defending Britain required legions of interceptors flying continual, exhausting patrols, attempting to locate enemy formations based only on visual sightings or unreliable spotter networks. It was a strategy of attrition based on heroic, reactive fighting.
The true defense, however, was already in place, standing as a skeletal, almost alien network of steel pylons along the eastern coast, Chain Home.
These massive aerials, sometimes towering 400 feet above the churning gray North Sea, looked like industrial cathedrals built to capture the wind. They were silent sentinels, transforming the invisible world of radio waves into hard, tactical reality. The operations rooms deep within the ground nearby offered a stark contrast to the wind-swept desolation outside. They were dimly lit, sterile spaces, dominated by large plotting tables, overlaid with maps bearing the rough texture of coarse paper.
Here, young women and men, the new vanguard of defense, sat glued to cathode ray tubes, their faces illuminated by the flickering emerald green trace lines.
When a high-frequency pulse of energy was sent screaming out over the English Channel, they waited for the minuscule echo that signaled the presence of the Luftwaffe formations, sometimes hundreds of miles distant, still invisible to the naked eye. This nascent detection technology was a pure electrical innovation that directly shattered the entrenched experience of the bomber doctrine. The German High Command operated under the belief that massed surprise attacks were fundamentally unstoppable. Their doctrine did not account for a technological leap that provided the enemy with 40 minutes of warning time. The invisible waves of Chain Home transformed the battle for the skies from a haphazard dogfight into a carefully choreographed system of interception. It allowed the heavily outnumbered RAF to concentrate its precious few squadrons precisely where and when they were needed. Instead of flying perpetual, exhausting patrols, pilots could wait on the ground, engines cold, until the green traces on the screen gave them the precise coordinates, altitude, and trajectory of the incoming threat. This was the first monumental victory of innovation, electrical ingenuity overriding established doctrine of massed attack. It gave the outnumbered defenders eyes across the channel, tilting the balance just enough to survive the Battle of Britain. As the war progressed and the fighting shifted from desperate defense to strategic offensive, the focus moved from electrical physics to material science. The prevailing wisdom regarding combat aircraft, rooted deeply in the experience of the biplane era and refined by early Messerschmitt and Spitfire designs, prioritized armor plating and heavy cannon caliber. The underlying assumption was that any aircraft designed for long-range operation especially bombing or reconnaissance, had to withstand significant punishment and return to base riddled with holes, relying on thick metal skin and self-sealing fuel tanks. Then came the de Havilland Mosquito. This aircraft was a magnificent anomaly, a speedster that defied every existing military expectation. Its body was not of riveted aluminum, the dominant metal texture of the war, but of pale birch and balsa wood. It smelled faintly of glue and varnish, a ghost among the heavy, oily aluminum giants. British officials had initially dismissed the design as too delicate, a flimsy contraption incapable of surviving the European theater. But the engineers had focused on a single, uncompromising principle: velocity. The Mosquito was stripped of heavy armor and unnecessary defensive weaponry. Its survivability relied entirely on its lightness and the phenomenal power generated by its two Rolls-Royce Merlin engines, which gave it unparalleled speed and altitude capability. In the cold, high atmosphere above occupied Europe, the Mosquito was a pale wooden ghost flitting above the ceiling of most contemporary interceptors. It consistently outran the heavy, metal-clad Messerschmitt Bf 109 and the formidable Focke-Wulf FW 190, whose designers stubbornly prioritized heavy machine guns and large-caliber cannon over sheer velocity. When a German pilot spotted a Mosquito, the challenge was not fighting it, but catching it. A German interceptor, laden with cannons and armor, would engage in a laborious climb, only to watch the twin-engined wooden wonder pull away into the thin air, disappearing from sight. It became a high-altitude bomber, a reconnaissance asset, and later a devastating night fighter. It survived not by absorbing bullets, but by rendering itself practically untouchable. The material innovation of prioritizing wood and speed over traditional metal and armor proved a decisive technological pivot, showing that sheer velocity, a product of material science, was superior to entrenched doctrines requiring durability and defensive armament. It was the material ghost beating the heavy metal fighter. Simultaneously, a revolution was occurring, not in the aircraft itself, but in the ordnance designed to destroy it. For decades, anti-air fire had been a practice of speculative guesswork. Naval guns and ground-based artillery crews tracked fast-moving targets, often only visible as distant, flickering dots in the sky. They relied on complex, mechanical, analog computers to calculate altitude, speed, and trajectory. They fired shells set with a simple time delay fuse. The high-altitude interception failed. A dark plume of shrapnel blooms harmlessly hundreds of yards beneath the silent target. This resulted in massive barrages, the sky filled with arcing tracers, and the heavy, continuous sound of guns, generating huge expenditure of ammunition for very limited results. The solution emerged in the form of the proximity fuse, a triumph of miniaturization and ruggedized electrical engineering. These were not mere time-delayed explosives. They were tiny, self-contained radar units embedded within the nose of an artillery shell. They were designed to withstand the immense centrifugal and longitudinal G-forces, tens of thousands of times the force of gravity, exerted during launch. The engineering challenge lay in creating vacuum tubes and circuitry that would not collapse or short-circuit under such violent stress. Once stabilized in flight, the minute electronic heart of the shell began emitting a radar signal. As the shell passed close to a target, an aircraft hull, the skin of a flying bomb, the signal reflected back, triggering detonation at the optimal distance. This transformed anti-air fire from speculative trajectory calculation into lethal precision. The visual spectacle was immediate and terrifyingly efficient. Instead of scattered puffs of smoke, The proximity fuse filled the sky with dense, instantaneous clouds of shrapnel. These appeared precisely beside the target, often without the need for sophisticated altitude or range calculation from the gun crew.
The impact on naval defense, particularly against the relentless onslaught of Japanese kamikazes and German V-1 flying bombs, was profound.
A single ship, previously relying on volume fire that might only achieve a hit for every 1,000 shells fired, suddenly possessed artillery that made every shell count. The experience-based reliance on human calculation, complex sighting mechanisms, and time delay fuses was instantly made obsolete. This was done by the tiny, clicking electronics packed into the shell's nose. The proximity fuse automated lethal intent, guaranteeing that material science and electrical ingenuity surpassed the limitations of human reaction time and predictive mathematics. It eliminated the guesswork, rendering traditional anti-air defense archaic overnight. The focus then pivoted from the air and sea battles to the largest logistical challenge of the war, the sustained amphibious assault. For centuries, military experience had dictated that landing an invasion force on a hostile shore was one of the most difficult and casualty-heavy operations imaginable. Defense dogma relied on the fundamental difficulty of transferring heavy equipment and masses of men from deep-water transports onto dry land. Successful landings required securing a port or harbor, which were, naturally, the most heavily fortified points on any coastline. D-Day, June 6, 1944, defied this historical difficulty, thanks in large part to the deceptively simple invention. This was the flat-bottomed, roaring landing craft, known best by the name of its creator, the Higgins boat. Andrew Higgins, an unconventional boat builder from New Orleans, had designed the vessel not for the high seas, but he designed it for navigating the shallow, obstacle-ridden marshlands of the Gulf Coast. His LCVP, Landing Craft Vehicle Personnel, was the antithesis of traditional naval design. It was cheap, mass-producible, shallow draft, and ruggedly built from welded steel. The sensory details of the D-Day approach were dominated by the deafening sound and smell of these small crafts. The pervasive odor of diesel fumes mingled with the salt spray and the visceral stench of fear. Thousands of these flat-bottomed vessels, their engines roaring at high throttle, churned toward the Normandy beaches. The texture of the LCVP was rough, utilitarian welded steel, designed to take punishment. It was designed to run straight up onto the sand without capsizing or fouling its propeller. The genius lay in the frontal ramp. This single feature fundamentally broke the enemy's reliance on stationary coastal defenses. The German defense strategy was steeped in the experience that enemy forces would inevitably bottleneck at key docking points, or they would rely on precarious transfers from small boats to the shore. The Higgins boat negated this entirely by allowing troops, jeeps, and crucial supplies to be disgorged directly onto hostile sands, rapidly deploying men and material anywhere along miles of coastline. The flat-bottom design meant they could traverse heavily mined and shallow water that would instantly halt conventional vessels. The rhythmic, heavy clang of the steel ramp slamming down onto the wet sand became the sound of the Allied victory. The LCVP transformed the impossible into the routine. It was a logistical innovation, simplicity, mass production, and direct delivery that bypassed centuries of accumulated experience. Regarding naval maneuvers and coastal fortification, rendering the heavily fortified European Atlantic Wall fundamentally vulnerable, the flat-bottomed boat beat the heavy concrete bunker. Finally, the story of innovation beating experience retreats from the noise of the battlefield to the hushed, clicking halls of Bletchley Park. The central hub of Allied code-breaking, here, the war was fought not with metal or explosives, but with pure abstract thought.
The German military operated under the deep-seated experience and conviction that their Enigma cipher machine provided cryptographic invulnerability. Enigma's complexity, the constantly changing rotors, plug board settings, and multiple permutation choices represented the pinnacle of abstract mathematical defense. The belief was that only human intellect and mathematical genius could ever hope to break such an intricate system, and then only sporadically.
Bletchley Park was a landscape of stark contrasts. Outside, the collection of unassuming huts suggested a quiet academic environment. Inside, the analysts worked in cold, dim light, surrounded by the rough paper of charts and the scratching of pencils, wrestling with abstract codes. But the true power resided in the machine rooms, a metallic, oily, and intensely loud environment,
where mountains of mathematical experience were undone by sheer mechanical force, the bombs.
Developed primarily by Alan Turing and Gordon Welchman, the Bombays were vast, relentless electromechanical contraptions. They did not attempt to solve the code through human insight in the traditional sense. Rather, they used focused engineering to systematically test every single possible setting combination of the Enigma machine at blinding speed.
Visually and acoustically, the Bombas were hypnotic. They stood as huge banks of cabinets, interconnected by tangled bundles of wires,
dominated by rows of rapidly turning, shiny metal drums. The atmosphere was dominated by the ceaseless, clattering mechanical symphony, the incessant clicking, ticking, and whirring of the gears and rotors performing tens of thousands of logical operations per second. The bombs were an application of mechanical brute force to an abstract problem. They transformed the intellectual puzzle of abstract encryption into a physical process of electrical elimination. Experience suggested that only a genius could break the cipher. Innovation provided a machine that could perform the work of 10,000 geniuses simultaneously and tirelessly. The Bombays systematically tore down the perceived cryptographic wall of Enigma, revealing that focused, relentless engineering. The power of mechanism and electricity was decisively superior to the complexity of abstract human design. This intelligence provided the Allies with tactical foresight that shaved years off the conflict, proving that mechanical force could conquer even the most intricate systems of human thought. In each of these 5 moments, the trajectory of the war was altered not by adherence to entrenched historical military wisdom, but by radical technological pivots. The silent electrical pylons of Chain Home surpassed the doctrine of massed air attacks. The pale wood of the Mosquito outran heavy metal armor. The tiny, ruggedized radar of the proximity fuse eliminated the need for predictive human calculation. The simple, roaring steel of the Higgins boat rendered centuries of coastal defense doctrine irrelevant, and the whirring, clicking Bombays dismantled the intellectual fortress of abstract cryptography. The Second World War was ultimately a decisive demonstration that in the rapidly changing landscape of the 20th century, experience could only carry a nation so far. Before the engineer, the physicist, and the unconventional thinker irrevocably changed the rules of engagement.